Hello, my name is Charlie Titchener. I represent the International Function Point Users Group. And now we're going to go into the second part of the set video 3A and 3B and talk about how to size an algorithm, which is a non-functional part of software user requirements. An algorithm is not what the user wants, which is a functional user requirement, but it is how to produce what the user wants. And the user wants some sort of a report or some sort of an output. So when we do algorithms, you may find that it requires a lot more work effort and a lot more schedule time to produce than the other two examples that we showed in video 3A, although the number of function points associated with the report, it might be the same, which in the examples that we're using are just 4. So with that, I'll get started and share my screen. And again, this presentation is an adaptation from the IFPUG International Software Metrics and Analysis Conference 19, presented in June of 2022. Now in 3A, just as a refresh, we had 3 reports: a sales report, which was worth 4 function points. It was very simple. It could be done with a 4-function calculator. The height of a cactus plant, which was a little bit more complex. It needed a scientific calculator. Also, we could have used the non-functional general system characteristics with a modified value adjustment factor. And instead of measuring it as 4 function points, 4.1 function points, which would give it a little bit more money, a little bit more budget, and a little bit more effort time in order to produce. Now let's look at a third problem that we want to calculate the highest profit. And again, the third level of complexity is an algorithm, which is a set of mathematical calculations, but they have to be done in a certain logical order. Now here are some examples from business, mostly business, that are in the Assessment Practices Manual representing algorithms. If you're in a different industry, you're probably familiar with an entire host of different algorithms. I mean, they're all over the place. Now here's a business example. This problem is taught in graduate schools of business. The point here is not to explain how the algorithm works. The point here is to emphasize that it requires a specialist in the field to solve these kinds of algorithms. Now, even though this is a beginning level algorithm in graduate school, in the real world they are much more complex. This uses a form of what's called Gaussian elimination in linear algebra. There are probably several ways of doing this. I'm going to just show you one way of doing it. Like I say, other people may do it different ways. Now, in order to count the snap points, it doesn't require solving the algorithm first. We go into the Assessment Practices Manual under subcategory 1.2, and the first thing that we do is we look for the complexity of this algorithm. I'm going to assume, for purposes of this presentation, that all of the data needed to execute the algorithm is in one logical file. In other words, in this case, let's put all of the data we need into one table in the database. Then we're going to calculate how big is this algorithm? What's the size of the algorithm? And we're going to take T times the number of data element types. Now remember, in the last video, we talked about DETs. A data element type can be a piece of data, it can be a mathematical operator, it can be a piece of control information, something like that. Now here's the problem. A company produces 2 products, let's call them F and S, and there are 3 types of materials that are needed to produce F and S. 20 units of material 1 are available, and we allocate 0.4 for each F produced and 0.5 for each S produced. There are 5 units of material 2 available, allocated 0.2 units per S produced, and there are 21 units of material 3 available, allocated 0.6 for each F and 0.3 for each S. The company makes $40 profit for each F and $30 profit for each S. With these resources, what's the maximum profit that the company could achieve? This is solved by the linear algebra. So here are the equations here. And over here is just a table where we're going to just keep track of things as we go along to solve the problem. So let's count now the number of data element types. First of all, up here, I want to tell the computer I want to maximize the profit. I don't want to minimize the profit. This is an optimization problem, so I want to maximize it. So this is 1 DET. And the last column represents the materials that we have to produce F and S. It also represents the profit. So this column here is 1 data element type. Now the 7th column represents the amount of material available, like there are 20 material 1s, 5 material 2s, and 21 material 3s. Also, before we start production, we're at 0 profit. I mean, we haven't produced yet, so we haven't made any profit. The first 2 columns are the 2 products that we're going to produce, F and S. That's 2 DETs. The 3rd, 4th, and 5th column represent how much material is in inventory. So before we start producing, we have 100% of material 1 in inventory, 100% of material 2 in inventory, 100% of material 3 in inventory, and 100% of our profit is 0 because we haven't started yet. So we have, in green here, we have 4 DETs. Also, over here we have mathematical operators. We have to tell the computer that we can't use more than 20 material 1, we can't use more than 5 material 2, no more than 21 material 1, and we have to tell it you cannot produce less than 0 F or S. Now that's obvious to a human, but it's not obvious to a computer, so we have to program that into it. So let's count up the number of DETs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the SNAP count, we have a low complexity algorithm. We have 3 times 10 DETs. So we have 30 SNAP points. So the size of this particular product here, of this report, is 4 function points and 30 SNAP points. And again, here's what the final solution looks like after the algorithm is solved. 100% of the profit is equal to $1,600. Now the following pages are text materials to explain to students how to solve this. I'm just going to flip through this, but the point is to see how much more complex it is to perform this calculation rather than the first 2, which is a simple addition, and then for a high school student in taking trig, a relatively simple trig problem. And 100% is 1,600. So we have this one field, 4 function points at 1,600, but it costs a heck of a lot more to develop than the other 2. If it's unresolved whether to use logical or mathematical operations, use logical operations. And be sure to count SNAP subcategory 1.2, especially algorithms with a software developer or somebody on the development team who's very familiar with the contents of that logical or mathematical operation. Don't get a pile of paper this tall and say, okay, somebody gives this to you and say, okay, count the algorithm. Don't do it that way. Have somebody go through it with you. So the first 3 sets of videos in this series have covered a quick introduction to the SNAP methodology, a definition of the 4 categories and 14 subcategories, a 2-part example of how SNAP works, and to show how SNAP accounts for the extra work effort for algorithms. And the final video of the introductory series will summarize these and provide some important extra information for you. So don't forget to see the final slide for video 1 for the references for these 4 sections and for these 4 videos. And I invite you to go to video 4.